Hi everyone, I'm Amrita Naina from Sri Venkateswara College of Engineering from the Department of Electronics and Communication Engineering. Today I'm going to discuss a topic called wireless laser power transmission. This is the seminar topic that I've opted for. So today we are going to discuss the introduction, history, methodology, block diagram, flow algorithm, application, resultant references. Let us get into it. So firstly, what is laser power transmission? Laser power transmission is considered a potentially efficient way for delivering the power through long distances in a wireless medium and has harsh hazardous environment conditions. So laser power transmit technologies has gained significant attention in recent years due to its potential to revolutionize energy transfer in a more efficient, safe, and eco-friendly manner. Uh, since we all know that the ever-increasing need in the electronic items and the ever-increasing need in the power um, consumption, it is very important to develop new means through which we can effortlessly transfer power from from one place to another. So now let us discuss the history of wireless laser power transfer or wireless power transfer. So firstly, the wireless power transfer was first introduced where small distances of power can be transferred through the theory of electromagnetism that was introduced by Maxwell in the year 1865. So it mentions how electromagnetic waves moving in the speed of light and concluded that light itself was just a wave. And then in 1886, Hertz performed experiment with the pulsed wireless energy transfer. We also know that there is uh, an experiment that Tesla wanted to do. He wanted to build a wireless power transfer tower in 1899, which was not completed due to lack of funding, but it could transfer energy about 16 its magnifying transmitter was measured 16 meters and could transmit tens of thousands of watts over without wires. So it also managed to light 200 lamps without wires from 40 kilometers away. So now let us discuss the methodology. So laser power transmission includes three parts, that is laser power emitter, laser power transmission, and receiver. So firstly, the laser power emission emitter has three components in which laser source, which is the main component, it generates the laser through which the energy can be transferred. And then there will be a aiming rotary table which directs the laser where exactly it should be aiming. So now there is a laser power transmitter where the transmission medium will come under. The efficiency of laser power transmission can be influenced by various factors such as reflectivity of optical components, absorption and scattering of the transmission medium, and aiming accuracy errors. So the next one is the laser power receiver. Receive the energy transmitted from the laser source. So firstly, the laser source emits the laser light that will be traveling through the transmission medium, and then there will be a laser power receiver, which is usually a solar grid or uh, which converts the energy into photovoltaic effect and gives us the power. So it converts an electric energy signal that can be used for power supply or charging. So there are different types of lasers that can be used. So we are here discussing two. One is the diode pump solid state laser. So these diode pump solid state lasers can be designed to emit at various wavelengths, allowing optimization for atmospheric conditions and photovoltaic receiver material selection. So according to this, we can select the type of material for the photovoltaic receiver, and also the narrow beam divergence and focus achievable with diode pumped solid state lasers minimizes the energy losses due to beam spread, and also these tend to be smaller compared to others, hence they are more portable. Next one is the novel semiconductor lasers, where the vertical cavity surface emitting lasers VCSELs are highly efficient, compact, and can be fabricated into large arrays. There is also quantum cascade lasers, operate in mid infrared and far infrared ranges, and also pumped semiconductor lasers combine the advantages of both, and with novel gain media materials. So this is the block diagram of the laser power transmission, where there is a transmitter block and the receiver block. In the transmitter block, we have the laser diode, which is going to the beam director. So the beam director will concentrate the beam and sends it to the photovoltaic array. So now the work that photovoltaic array does is to convert the energy, that is a light energy, into electrical energy through a and then is sent to the power controller, where we get the DC voltage, which is given to the battery or the load. All these are controlled by the control systems. So let us see the flow algorithm of this. So firstly, the power source, that is a solar panel array or a generator or power grid that is in the space. It can be for like a solar panel array. So let us consider a solar panel array which is receiving the solar energy. So this is the power source. The next one is the laser conversion. This will be converted into laser beam of specific wavelength. For example, a near infrared using a laser diode or other excitation systems. Next one is the beam shaping. Use lens or mirrors to collimate the laser beam, minimize its width or width for efficient transmission. So we want a beam which has less width, so that it can be concentrated at a particular area, and also beam directing, which will direct the beam exactly to the receiver unit. And then the beam capture, where the photovoltaic cell array is in the receiver captures the laser light. Here again we'll have a photovoltaic cell array, so it converts the light energy into the electric energy. And the next step is the conversion of an energy to electricity, so that we can that can be used and saved. So where are the applications of these laser power transfers? The major application is in the solar power transmission, where there are large satellites that can capture the solar power and send the energy to Earth, and can be converted into electricity for more use. This is more convenient because solar power that is received on the Earth's surface might be discrete due to atmospheric changes, or during the night we won't get the solar energy. It is more convenient to transfer the solar energy directly from space and send it to Earth. So there is one application that is there are three types of applications: ground based, and through water, and to space. So firstly, ground based LPT, where it signifies the a process that has been made, and under the support of research work such as development of high efficient lasers, enrichment of energy transmission theory, and development of energy receiving devices. So as a result, the energy conversion efficiencies of wireless energy transfer systems has improved significantly over time. Then We have the space applications. As I told, the space application where there will be a solar power satellite or a space station where it stays in a geosynchronous earth orbit, and to gather the solar energy and convert it into electrical energy. This electrical energy is then beamed to the earth using microwave or laser power. Here we are talking about LPT, so we'll be using the laser power for the transmission, and then received in the on the earth's surface. And then underwater applications, it is more important for the underwater applications, since in the underwater applications there are many machines that cannot use wires for the power consumption. So, underwater wireless optical communication is an emerging and feasible underwater wireless communication technology, which uses visible light carriers with blue-green spectrum regions to transmit information data in an ocean environment. So, the wavelength that they're using in underwater is about 450 to 560 nanometers wavelength, and the data was sent by the laser diode and received by a multi-element receiver composed of SPAD and a solar cell that decodes the transmitted symbols and harvests the electrical energy from the optical signal respectively. So next are the results. What are we expecting from this? So LPT has the ability to transmit power over long distances. It can deliver about kilowatts of powers over kilometers. Ideal applications are like powering drones, satellites, or remote sensors. Lasers can concentrate a large amount of energy into narrow beam, resulting in high power density, efficient power transmission even through atmospheric disturbances like fog or rain. Advancements in beam tracking and point stabilization technologies are essential. Developing and deploying high powered lasers and sophisticated optic systems are currently expensive. Cost reduction strategies are necessary for broader economic feasibility. So these are the reference papers that I have referred. Thank you for watching the video.